So in this video, we will see applications of our compactness result in reflexive Banach spaces. So we know that sets that are convex, closed, and bounded are weakly compact. What we want to get is the ability to extract a weakly converging subsequence from a bounded sequence in such a set. Now, this is not a direct consequence of the weak compactness because we don't know in general whether or not the weak topology is metrizable. In fact, it won't always be metrizable. So we cannot infer the sequential compactness, the ability of extracting weakly converging subsequence from the weak compactness. However, it happens to be true, and we will prove that in proposition 9.8. So we'll prove that every bounded sequence in a reflexive Banach space has a weakly converging subsequence. And the reason for that is that the topology, the weak star topology on the dual of a separable space is metrizable. That's a result we've seen in the previous chapter. So exploiting that and the fact that we're only looking at one sequence, which is a countable set in itself, will allow us to exploit some separability, get some metrizability of the weak topology, and derive from that the weak compactness implies a weak sequential compactness in this situation. So this is the first thing we'll prove, and this allows us to start extracting weakly converging subsequences, which is something very helpful in proving existence theorems. And indeed, as a corollary, we'll prove the existence of a point on any convex, closed, and bounded sets that realizes the distance between any x outside this compact set and the compact set, right? Normally, such a distance is defined by an infimum, but this infimum will actually be a minimum. Now, that looks like a projection onto such a convex, closed, and bounded set, which is a central result that we have in Hilbert spaces, right? The existence of a projection onto convex set. Now, here, well, first of all, our sets will have to be bounded, convex, and closed. But the problem is that this y here that we would like to be the projection won't in general be unique. So we'll need to make a little detour and talk about uniformly convex Banach spaces. This is a class of Banach spaces that's a little smaller than the class of reflexive spaces. These are some of the nicest reflexive spaces, but this includes, for instance, all of the LP spaces where P is strictly between 1 and infinity. And we will finish off this video with a theorem that tells us that indeed in a uniformly convex Banach space there exists a unique element that realizes the distance to a closed convex bounded set, and that's what we call the projection onto the convex set K. And such an existence of a projection map is critical in solving optimization problem. If you go back to the first 2 weeks of the course, you would appreciate that the Stompakia theorem, the theorems that we use to produce existence and uniqueness result for PD in particular, but not only, more generally the ability of solving some optimization problem in Hilbert spaces really came from the existence of a projection onto convex set. And what we're seeing now is that exploiting the appropriate weak compactness in a uniformly convex Banach spaces, we will also have a well-defined projection onto convex closed bounded sets. But first things first, we need to move from weak compactness to a form of weak sequential compactness and the ability of extracting weakly converging subsequence from bounded sequences. Let's do that first. Okay, so let's start with a bounded sequence, Xn. And then consider the subspace that is defined by taking the span of this Xn and taking the closure of that in the Banach space X. So this is a closed subspace and it is separable. That's the closure of a span of a countable set. So it's a closed separable subspace of X, and therefore it is a separable and reflexive Banach space, right? Because we've seen that reflexivity goes to closed subspaces. Right. Now, I would like to have the fact that y star is separable, but I cannot directly derive it. I will prove it in a minute. But let's just assume for a second that it is. If y star is separable, so let's keep the if in a box such that we remember that we're going to need to prove that, then what happens? Then the unit ball of the dual of y star, which is y double star, endowed with the weak star topology, is metrizable. But what is the unit ball of y double star? Well, y double star can be identified with y because y is reflexive, and when you do that identification, this unit ball with the weak star topology, which is really having y star act on y double star, you have y star act on y by making the identification, and this is the weak topology, as we've also seen in the case of reflexive Banach spaces. The weak star topology and the weak topology coincide. So this unit ball of y with the weak topology is metrizable, and therefore you have a weakly compact set for metrizable topology, so you can extract a weakly converging subsequence. Okay, so that implies the result. So it suffices to show that y star is separable, knowing that y is separable and reflexive. So okay, so we'll show that y separable and reflexive implies y star separable. Okay, so here is how we do this. We pick a set, let's call it yn, of elements in y set that is dense in y. Okay, we can do that because y itself is separable. Now we see y as y double star through the identification, and so we can then pick xn, a sequence in, or let's call it yn star, in y star to the n, such that yn star applied to yn almost realizes the norm. So let's say this is greater than 1/2 times the norm of yn itself, right? And of course I'm picking those in the unit sphere of y star. So it suffices to show that the yn star, if I take their span and the closure of that, I get all of y star. That's going to give separability because you could take the span not with R as the underlying field, but with the rational as the underlying field, and then you would have a countable dense subset of y star by taking that span. So this is all we need to prove. And how do you prove such a thing? Well, you define, let's say, Z to be the span of the yn star, okay, and we need to show that the perp, actually, sorry, the closure of that, and then we need to show that the perp of that is 0, right? We've seen before that this would imply density. Okay, so how do we do this? You take a element, so the perp of that will be in y double star, which you can identify with y. So let's take a z in z perp, and then we have that z tested on yn star is 0 for all n. Okay, and then given an epsilon, we're going to pick n in n such that z minus yn in norm, the norm in y, which is also the norm in x, is smaller than epsilon. And then what can I say about the norm of yn? So remember that 1/2 of the norm of yn has to be smaller than yn star applied to yn. And then what I can do is add and subtract z. And so this is yn star, yn minus z, plus yn star z. But okay, yn star z is 0. So this is just yn star tested on yn minus z. And that tells me that 1/2 of yn has to be smaller than the norm of yn star, which is 1 times the norm of yn minus z, which is epsilon. So this is smaller than epsilon. And now, okay, but what does that tell me about my z? Well, my z therefore has to be smaller than 3 epsilon, because yn is smaller than 2 epsilon, z minus yn is smaller than epsilon, so z is smaller than 3 epsilon. And epsilon was arbitrary, so z has to be 0, and my z was arbitrary, z perp, so z perp is trivial, and that means that z is the whole space, so z is equal to y star, and we've proven that y star is separable. And that concludes the proof, because under the assumption that y star was separable, we were able to extract a weakly converging subsequence from our original bounded sequence. And in passing, we've proven that the dual of a reflexive separable Banach space is also reflexive and separable. And that concludes the proof of this proposition. Now, as a corollary of this proposition, we can prove corollary 9.9 that tells us that for every x in X there exists a Y, not necessarily unique, in K, where K is a closed bounded convex set that realizes the distance, such that the distance between X and K is exactly the norm of X minus Y. Now, the way you prove that is as follows. You pick a sequence of point in K that is such that x minus yn tends to the distance from x to k. Let's call that distance d, as n goes to infinity, right? Now that's a bounded sequence because k itself is bounded anyway, and so we can extract a weakly converging subsequence by the proposition 9.8. So there exists a y, priori it's in x, such that yn tends weakly to y. Now, k is weakly compact. So in particular, it's weakly closed. So if I have my yn that converges, a subsequence, if I have a yn k that converges to y weakly, then this y has to be in k itself. Right, now I claim that this y does the job. Now let's see that. So what we have, well, we have that x minus y is certainly greater or equal to d because y is in k. And for any epsilon, if you go far enough in your subsequence, what do you get? Well, you get that x minus y and k almost realize the distance. So it's smaller, say, than 1 plus epsilon times d. And what is that saying? Well, it's saying that for every epsilon far enough in the subsequence, x minus y and k will be in 1 plus epsilon times the unit ball of your Banach space. Yeah, but this is a weakly closed set. So if it's a weakly closed set, you take a weak limit and it has to be in the set. And so what we get is that x minus y is in 1 plus epsilon d dx for every epsilon. And that exactly means that x minus y is smaller than 1 plus epsilon d for every epsilon. And so x minus y in norm is exactly equal to d. Okay, so we do have a point that realizes the infimum. We get it by taking a subsequence and approaching the limit and using the weak compactness. However, we are not sure that this point is unique. So now we're going to study a subclass of the reflexive Banach spaces called the uniformly convex Banach spaces, and we'll see how a strengthening of the reflexivity condition guarantee the uniqueness of the Y in this corollary. So what is a uniformly convex Banach space? It's a Banach space which unit ball is very nicely and uniformly convex in the following sense. If you have 2 points on that unit ball and they're not too close to each other, then their midpoint, the point in the straight line between x and y, straight right in the middle, has to be a fair way away from the unit sphere. Now here's the way you should picture this, right? Imagine this is your unit sphere and you have a point x here and a point y there, and you look at the middle point, x plus y over 2, see it's reasonably within delta, say, away from the unit ball, from the unit sphere, the boundary of the unit ball. Now, on the other hand, if your unit ball has like a flat face, something that looks like this, and you might have 2 points here, right, that are epsilon apart, but their midpoint is exactly on the boundary of the unit ball, on the unit sphere. So x plus y over 2 in norm is equal to 1. It's not smaller than 1 minus delta, despite x minus y being greater than epsilon. So the uniformly convex Banach spaces are balls that are sufficiently round to guarantee this little distance of the midpoint from the boundary, and it guarantees that in a uniform way. That is to say that the relationship between epsilon and delta here is independent of the choice of point that describe where you are on the unit ball. So this very geometric condition of uniform convexity of the norm happens to imply reflexivity. So this is really geometry of Banach spaces. It's geometry of the norm implying a more algebraic and topological property, which is reflexivity. We will prove that in theorem 9.11. So the class of uniformly convex Banach spaces is a subclass of the reflexive spaces. And this is exactly the refinement we need to guarantee uniqueness of the projection onto a convex closed and bounded set. We'll do that in theorem 9.12. Now, this is the starting point of an entire theory where we could describe more geometric properties of norm and understand what they tell us about a Banach space. You should be asking yourself, well, how large is this class of uniformly convex spaces? What happens if I have a norm that is not uniformly convex, but that is equivalent to a norm that is uniformly convex? Well, this is a whole world in itself. One of the things you would prove is that the LP spaces, at least, are uniformly convex, that they are reflexive spaces that are not uniformly convex, but these spaces are already fairly exotic. And then you would like to think about how these properties dualizes, and it doesn't dualizes directly. There's a notion of uniform smoothness that is in duality with the notion of uniform convexity. This is a world in itself. This is what's called the geometry of Banach spaces, and we won't go far into it in such a first functional analysis course. But let's prove that at least this property is indeed a refinement of reflexivity, and it gives us the missing ingredient to do optimization, namely the uniqueness of the point y. So let's prove theorem 9.11. We're going to do that by contradiction. So we're going to pick an x double star in the unit ball of the bidual, and we're going to pick an epsilon by contradiction. And we're going to pick an epsilon such that if I take any x in the unit ball of x, its image through the canonical embedding of the unit ball of x into the unit ball of x double star is reasonably far from x double star, right? So you can do that if the unit ball of x double star is not the image by I of b of x. Okay, now given that epsilon, I'm going to use uniform convexity, and I'm going to pick the delta that corresponds to that epsilon. So the delta such that for all x and y in x, whenever x minus y is greater than epsilon, I'm going to be able to guarantee that x plus y over 2 is greater than 1 minus delta. Okay, so I've picked delta in that way. Now I want to find an element in the unit ball, actually here, let's take it in the unit sphere to avoid confusion. And here, let's take that in the unit sphere of x star. That almost reaches the norm of x double star. So such that x double star applied to x star is close to 1. And the notion of closeness will depend on delta. So I'm going to put that greater than 1 minus delta over 2. Now, I want to define a neighborhood in x double star. So I'm going to pick the V to be the set of y double star in x double star that are close enough to x double star when tested against just that element x star. Right, so such that this is smaller than delta over 2. So V, that's a weak star compact, sorry, not compact at all, it's a weak star open, it's a neighborhood. It's a neighborhood of x double star in the weak star topology of x double star, testing against a single element x little star, x star. And so it's a weak star open set in x double star. Right, now remember that the image of the unit ball of x in the unit ball of x double star is dense. That's what's called Goldstein lemma. So Goldstein lemma tells me that IBX, well, it's dense. So if I intersect it with an open set like V, I have to get a non-empty intersection. Cool. So I'm going to pick an X now in the unit ball of X that is such that I of X is in V. Right? I can do that thanks to Goldstein lemma. Now, what can I say? Well, remember that I of x cannot be too close to x double star, right? Because, well, this was the starting point of our contradiction argument. Every element I of x has to be epsilon away from x double star. So now you can define another weak star open set. So you can define W to be I of x plus epsilon times the unit ball of x double star, and you take the complement of that. So you've just shifted a weak star closed set, thanks to Mazur's theorem. So the complement of that is weak star open. Now, again, it's always in x double star that we talk about this weak star topology. Now, what does Goldstein lemma tells us again? So it tells us that the image of Bx intersected with V and intersected with W has to be non-empty. So I can pick a Y in the unit ball of X such that I of Y is in V and is in W. So it's epsilon away from Ix, and in the meantime it's in V. So it's fairly close to X double star from the point of view of X star. Now let's put all of these things together. What do we get? Well, we get that X star tested against Ix minus X double star. That's smaller than delta over 2. That's because Ix is in V. Now, in the meantime, we have that X star Iy minus X double star is also smaller than delta over 2 because Iy is in V. But on the third hand, Ix, what have I got here? On the third hand, Ix minus Iy is greater than epsilon in the norm of X double star. Right. But that tells me that, because this is the same thing as the norm of X minus Y, and so this also implies that by uniform convexity that X plus Y over 2 has to be smaller than 1 minus delta. This is going to give a contradiction, because if I add up the first two lines, I get that x star times I x plus y minus 2x double star has to be smaller than delta. Okay, but that then tells me that 2x star x double star is always smaller than delta plus x star I x plus y, right? But now remember that this x star x double star here was chosen such that it was greater than 1 minus delta over 2. So we have 1 minus delta over 2 smaller than delta over 2 plus x star, and let's estimate that directly, plus norm of x star times norm of x plus y over 2. Okay, but that tells me that 1 minus delta is less than, well, norm of x star is 1, and norm of x plus y over 2 is smaller than 1 minus delta. And that is my contradiction, which concludes the proof. So uniform convexity implies reflexivity. Thanks to a large extent to Goldstein's lemma and the density of the image of B of x in the unit ball of x double star for the weak star topology. Okay, let's finish up with the proof of theorem 9.12, the existence of the projection on convex bounded closed sets in uniformly convex Banach spaces. Now, by the theorem 9.11 that tells us that such spaces are reflexive, and the corollary 9.9, we have existence, right? So we can guarantee that for every x in x, there exists a y in k, such that norm of x minus y is the distance between x and k. Cool. So all we need to prove now is uniqueness. So we assume that there exist two such y. So we fix an x, and then we have two y, y1 and y2, such that x minus y1 is the same thing as x minus y2, which is this distance. Let's call that d. And in the meantime, y1 minus y2 is non-zero. So let's say there exists an epsilon such that this is greater than epsilon. Right. Now, let's have a look at x minus y1 divided by its norm. It's a vector of norm 1 plus x minus y2 divided by its norm. That's another vector of norm 1, and they equal to 1 upon d times 2x minus y1 plus y2. On the other hand, if I look at the difference, of these two vector of norm 1, I get 1 upon d, the x's cancel, and I get y1 minus y2, which I know is greater than epsilon. So this is greater than epsilon over d. So I have 2 points here that are reasonably far apart, and so uniform convexity guarantees that their averages has to be a little bit away from the unit sphere. So there exists a delta such that 1/2 of x minus y1 divided by x minus y1 plus x minus y2 divided by x minus y2 has to be smaller than 1 minus delta. But we know what that is, so we know that this means that 1 upon 2d, or 1 upon d, times x minus y1 plus y2 over 2 has to be smaller than 1 minus delta. But what is that telling us? It's telling us that x minus y1 plus y2 divided by 2 is strictly smaller than the distance between x and k. And that is a contradiction because y1 plus y2 is in k. This is a contradiction since y1 plus y2 over 2 belongs to k by convexity of k. All right, so x minus y1, the average of y1 and y2, sorry, the midpoint between y1 and y2 has to be at least d, so it cannot be strictly smaller than d. And that concludes the proof. So in uniformly convex Banach spaces, sufficiently nice Banach spaces, we do have a well-defined projection onto closed convex bounded set, which is really the fundamental building block to be able to do optimization in such Banach spaces, and then all of the consequences of being able to solve some variational problems, including applications to PDEs. But we're going to leave that here for now, and in the next video we'll see some slightly different applications of PDE where we also exploit reflexivity and the Banach-Alaoglu theorem.